Good afternoon, and welcome to talk on what's new in TypeScript. My name is Anders Heilsberg. I'm a technical fellow in the developer division at Microsoft. I used to work on C#, but now I mostly work on the TypeScript project, which I've been involved with now for 7 years, probably. So for this talk here, this is sort of what we're going to look at. I'm going to give you a brief history and status of the TypeScript project. And then I'm going to talk, since I'm a type system designer, I'm going to geek out a little bit on the type system that we've designed for TypeScript. And then we'll look at some of the features that we've introduced in TypeScript over the last year or so, and also some of the features that we're working on for beyond that. And then finally, hopefully, we'll have time for some Q&A. So I'm sure you all sort of have heard us talk about how TypeScript is about making JavaScript scale. Someone had wrote a blog post at one point that said TypeScript, it's JavaScript with superpowers, which I think is sort of a good way of capturing it. It's all about making excellent tooling and more productivity for TypeScript or for JavaScript. That's really what TypeScript is all about. Our project got started. It's now been a while, so I thought it'd be fun to talk a little bit about how we got started and why we're doing what we're doing. It actually goes back to late 2010 or 2011, and at that point, the world of the web looked quite different, right? I mean, the predominant browser was Internet Explorer. Still about 50% of traffic at that time ran through Internet Explorer. CoffeeScript was like the new cool thing in the JavaScript space. Front end was dominated by jQuery, and back end, we had frameworks like Knockout and so forth. But a lot of changes were afoot at the time. ECMAScript had at that point finished ECMAScript 5. That was like in 2009, after sort of 10 years of not doing anything. The standards process was getting going again. HTML5 had happened, and also we'd gotten much better JavaScript VMs through Google's work with V8 and our work with Chakra. And the world was moving from a very homogeneous place, Windows everywhere, to a very heterogeneous place because of mobile, and everyone was looking at, there was sort of this perfect confluence of factors that all of a sudden made JavaScript incredibly relevant again. And we were seeing customers, both externally and internally, starting to write really large JavaScript apps and having a really hard time doing it because JavaScript was not designed for large apps. In fact, we were seeing teams like Outlook.com use tools like Script Sharp to write in C# and cross-compile to JavaScript just so they could get better tooling and type check. And we full well knew that, we can do a lot in our IDEs and in our tools, but we need certain things to be present. In particular, we need a type system to be present so we can actually reason about the code. So our idea at the time, and this is actually we have this OneNote of our old design notes, and this was one of our first official design meetings in January of 2011 for the Strata project, which it was called at the time. Where we tried to sort of outline some of the goals that we wanted to do. And you see that a lot of the things that we were talking about there are actually true today. It was about supporting excellent tooling and frameworks. It was not about extending JavaScript. It was about making sure that every JavaScript library could be used with TypeScript and so forth. We started working on TypeScript, and we worked for about 2 years internally, recruited some internal users as well, and finally shipped the project in October of 2012. And we knew at the time that in order to appeal to JavaScript community, we had to be open source. But open source was sort of a new thing for Microsoft at the time. This was a learning experience, right? And so we ended up putting TypeScript on CodePlex, which was our, the open source repository at the time. Here's actually a picture of the very first, from the conference where we did the very first public presentation of TypeScript. This is myself in the middle. There's Luke Hoban, which was our product manager, and then Steve Luco on the other side of me, who was at the time the architect of the Chakra VM in IE. And Steve actually wrote the first prototype compiler, and that was a port of the Chakra parser from our VM. With some added support for type annotations, and that was the one that we shipped in 2012. And then, of course, we went to work on producing a real compiler. In fact, we produced two compilers. First, we produced one that was we recruited some guys from the C# team, and we started writing a compiler, and we wrote it like you would write C# in JavaScript. A lot of classes, a lot of auto-generated syntax trees and whatever, and we had 50,000 lines of code before we even started writing anything, right? And that compiler, that was the 09 compiler. We did manage to implement generics in that one, and it was an interesting exercise. And it had some perf issues. And then we got interested in, writing it the right way. We were starting to really learn, what JavaScript is about. And there are sort of many styles of JavaScript, and there's a more functional style of JavaScript where you put functions within functions and closure over outer state and whatever. And we started experimenting with that and discovered that, boy, we could write a much faster and much smaller compiler that way. And that's actually the code base that we're on today. This is the one that lives on GitHub, because at the same time, we had also learned a lot about how to do open source and open development. And so we went to where the action is at on GitHub. We moved all of our development practices to be completely open. And this is where the team works today, day to day. We've been working on this same code base for the last 4 years. And it's going great. We've got lots of releases. We've got great community involvement and so forth. Now, later that year in 14, there was this interesting, I don't know if any of you remember, I've ever seen this slide. It was from the Angular conference, where Google was talking about the next version of Angular, Angular 2. And they had this one slide where they were talking about how they were going to build it. And they were going to build it in this language called TypeScript, which was like a thing that was bigger than TypeScript. And we were going, well, what's that? I haven't heard anything about that. And it turns out that it's basically JavaScript with type annotations, but also with annotations or decorators and introspection. And we go, well, we can do that. We could do that in the TypeScript code base, And so we talked to them and we said, why don't we come down and show you what we got and talk about what it is that you need. And we went down to Mountain View. We had a great engineering meeting with the Angular team. This is open source, right? I mean, you can do these things. And so lo and behold, about 4 or 5 months later, the Angular team actually moved their development to TypeScript, and a new Angular 2 is entirely built, and well, I think they're up to, I forget what version number they're up to, 5 or 6, or yeah. And that's been great. That I think, taught us, again, a lot about the importance of community and open source, and really it sort of brought us to our value system, if you will. We really value open source and open development, and you will see the entire TypeScript team is spending their time on GitHub. That's where we all live. We've also sort of evolved to a mantra of closely tracking the ECMAScript standard. We don't see it as our job to add new language features in the core language of JavaScript. That's what the ECMAScript Standards Committee does. And once there's a rigorous process for that, and once features reach stage 3, that's when we start implementing them in TypeScript, because there's a reasonable assurance that they'll make it into the final standard of the language. However, we do see the type system subset of the language as being our purview, and we are committed to doing lots of innovation in the type system. And of course, we we see one of our core assets being the great tooling that we can build because of these extensions. So building best-of-breed tooling is absolutely a core mission of ours. We all, most of our team use Visual Studio Code. How many of you use Visual Studio Code, out of curiosity? Wow, look at that. Yep, and you probably know Visual Studio Code is written in TypeScript. We have a great working relationship with that team, and so we are deep believers in dog fooding. Also, we're working hard to continuously lower the barrier to entry. I don't know if you knew, but in the last year or so in Visual Studio Code and Visual Studio, we have switched the JavaScript language service to actually be TypeScript. So even when you're coding in JavaScript in Visual Studio, the TypeScript compiler is actually sitting behind and analyzing your code and providing statement completion and so forth. And that means that it's the same tools it's just a matter of what the file extension is and whether you allow the type annotations to be in the language or not. And then finally, to paraphrase Bombers, developers, it's all about community. That's sort of how we want to work. And one, I think, excellent example of the community involvement in the TypeScript project is this repository called Definitely Typed. How many of you are familiar with what Definitely Typed is? Yep, lots of you. This is basically where the open source community is gathering all of the type definitions for programming in JavaScript on the web. You probably didn't know that last year, this was the most active repository on GitHub. 42,000 commits by almost 6,000 committers. Thank you, yeah. This speaks just volumes to what a motivated community can do, and we are deeply devoted to supporting this effort. We've built a lot of tools that we run in the cloud that because there's so many pull requests on Definitely Typed that someone needs to go in there and categorize them and find the main committers and find the main maintainers for each of the repositories and gets it, and get all the traffic, because otherwise it's just chaos. And so we devote a lot of time to that. We've built a whole bunch of tools that automatically publish all the type definitions to NPM. So all you got to do is really just submit a pull request. Once that's accepted, it automatically gets built and deployed to NPM in the @types namespace. And we'll see some examples of that in the demos. So that's just sort of one place where we care a lot about community. Another is the work that we've done recently with the Babel team. Babel is another transpiler out there done by Facebook, and it's used by like anyone who's doing development on the React stack of tools will probably be using Babel. And we recently had one of our devs actually submit pull requests to, in coordination with the Babel guys, to build support for TypeScript syntax in Babel, effectively support for erasing TypeScript syntax when you transpile using Babel, which means that with Babel 7, you'll be able to now use TypeScript as your type checker and Babel as your emitter. Basically, you just run TypeScript in no emit mode, and that just gives you statement completion and type checking and all of the wonderful features you want in VS Code, and then you can do your normal build processes using Babel. And that's going to be great. That's coming out in Babel 7, which I think is about to ship in the next coming months. Of course, we also are deeply committed to, in a sense, being the Switzerland of frameworks is how I talk about it. We've worked, obviously, very deeply with the Angular team, but we've done lots of work to better support React in TypeScript. We natively support JSX syntax and type checking of JSX, code refactoring, and so forth. And we've worked closely with the Vue community in the last year or two. In fact, the latest releases of Vue now have great TypeScript support. Evan Yu, the maintainer of Vue, wrote a a very nice blog post about it that you can go check out. So we're really committed to work, and of course there are other. I can't put all the frameworks up there. That's the wonderful thing about JavaScript. There's a new framework every month, right? So and many other of them like Ember and Glimmer and Ionic and Aurelia are all also in the game with TypeScript. In terms of adoption, it's really been quite phenomenal over the last. This is a graph of the number of NPM downloads of the TypeScript package over the last 3 years. And March, which is the last month here, was the first month where we rounded 10 million downloads in a month. And that compares to 5 years ago when we had 5,000 downloads in a month. This is a 200x growth over 3 years, which is quite amazing. And it seems to still be growing. So that's fantastic. Here I've tried to overlay all of the releases that we've had in the last 3 years, and as you can see, it's a pretty fast-moving team. In about a year and a half ago, we sort of committed ourselves to be on a 2 to 3 month release cadence, which tracks what VS Code is doing, and we pretty much kept up here. Like in the last, this slide shows there's 13 releases in 3 years. And it's just sort of this release train that keeps on going. There was there are all sorts of programming language ratings, but I thought it was cool to see us sort of crawl up in the top 10 programming languages, depending on which survey you look at. But we're up there with Go and Scala and Swift and so forth, and still crawling up. In fact, one interesting other statistic that someone told me was that last year there were more repositories created on GitHub with TypeScript as the language than there were C++ repositories created on GitHub. So we've sort of inched into the big leagues, which is great to see. On Stack Overflow there was a survey, and I was particularly pleased to see that we're sort of amongst the most loved technologies, which I think speaks to the fact that we serve a real need. I mean, this actually delivers real value. Lots of companies are using our stuff now. Google, of course, but Slack and Lyft and Reddit, GitHub, Netflix, et cetera. So. Final slide on the history and status is just a picture of our team. There's about, we're co-located with the JavaScript tooling team, so TypeScript and JavaScript is sort of all one big happy family. Like I said, everyone here is available on GitHub on the issue tracker there. You can just come talk to us, file issues or suggestions. We love interacting with the community. Okay, that's my sort of brief intro. Now we're gonna, if you don't mind, geek out a little bit on type systems and what it's like to design a TypeScript system for JavaScript. And TypeScript has a very different type system than anything I've worked on, which is what makes it fun as a language designer. It is gradually typed, which is in a sense a new discipline. It is structurally typed. It is also generic. It relies extensively on type inference. It uses control flow-based type analysis. And then we have a whole bunch of novel type constructors and distinct namespaces for types and values, so we can sneak all the types into JavaScript code without getting name conflicts. And so there's a bunch of things in there that are sort of solved in new and interesting ways. And in particular, the one at the bottom there, TypeScript is both object-oriented and also a deeply functional programming language. You can use all the mainstream functional programming techniques, and like some of our support for discriminated unions and union types and so forth is quite advanced. Now, the gradual type system thing, I think, is perhaps particularly interesting. You know, it was always the case, or at least it used to be, yeah, with TypeScript system research that it was all predicated on soundness. This notion that your type checker will not allow something that is as undefined behavior to get through the checker, right? Like you can't assign a pointer to an integer or because, I mean, that could be, or an integer to a pointer, because then you could access uninitialized memory and that would be bad, right? And so because type system research was sort of, in that sense, constrained, there was a lot of research that didn't actually happen that even so was interesting. And in particular, there was very little that happened in this space of gradual typing, because TypeScript, our type system is in a sense a Swiss cheese. It's full of holes. I mean, yes, but that's by design. You don't have to type everything, but the more stuff you give types to, the more we can help. And there are certain modes you can be in where nothing can be of type any, and then we can actually start to provide some guarantees. But it is not a requirement. And that means that there's a much lower threshold barrier to entry, right? And it also means that we can explore avenues of type system capabilities that no one has ever looked at because they just sort of deemed them unsound to begin with. But the interesting thing about where we work is that underneath it all, there's JavaScript. And JavaScript has meaningful semantics defined for anything you can do. You're never going to observe uninitialized memory or whatever. Now, the meaningful semantics might not be useful semantics, but they're well defined. Which means your programs are never going to behave in an unpredictable manner, no matter what you do, right? And because that is the case, it's actually fine to have a type system that doesn't prove everything to be sound, right? And once you do that, then all of a sudden you can explore all sorts of new areas that no one has ever gone to before. And that's actually what makes this really interesting, right? And really useful, it turns out. Now, I mentioned also here that the type system is structural as opposed to nominal type systems like, say, C# or Java, where you know, when in those nominal type systems, when you have a base class and a derived class, you know, you can only assign a derived to a base if it explicitly says that it extends that derived that base class. And likewise, you can only be treated as an interface if you explicitly say that you implement that interface. In contrast, there are structural type systems where, as long as you fulfill the contract by structure, as long as if an interface says you must have 3 methods, or 2 methods, foo and bar, and you have 2 methods, foo and bar, well, then you implement the interface without saying anything further. And that's actually a much, much gentler world for someone as a programmer to live in, because you know, you don't have to first overly specify the problem. You just go along with sort of this duck typing, if you will. But as a type system implementer, it also causes you to run into a whole bunch of headaches. Here, for example, is one really gnarly problem. Like, let's say you have 2 types, foo and bar, that are structurally identical, but are defined differently, right, or separately. And now let's say that you assign a bar of string to a foo of string. How does the type checker know that that is okay? Well, in a structural type system, the way you do it is you say, okay, well, let's see, foo of string requires you to have an item property. Does bar of string have an item property? Yes. Does it have the same type? Yes, there's string. That's good. Now let's look at the next property. Well, that's of type foo of string. Well, now we got to go make type foo of string. And now we have bar of string. And then, well, do they compare? Well, yes, they have an item property, and then we get to the next property. Well, now we make a foo of string and a bar of string. And off we go to the races, and it's, you know, it's turtles all the way down. And you end up in these deeply recursive, like crazy problems that you're staring at, and you know, as we went about implementing this, it's funny. We actually we ran into problems that apparently have no solution in known type systems. We talked to some of Microsoft Research has some of the preeminent researchers in type systems, and we talked to some of them, and they were like, no, we don't actually know a solution to that problem. It turns out that in order to do this stuff, you sort of have to cheat. And so we have this thing we call the turtle cutoff, where, if we see 5 levels of recursion that are manufacturing the same types, then we just stop, and then we say, let's assume that that's true. Now, if everything else is also true, then we're just going to say it's true. Because we don't have to be sound. We don't actually have to prove that this is true. It is just beyond a reasonable doubt, right? It turns out this works marvelously. It took the user community like 6 years before someone even reported a bug that was related to this. They had some crazy JSON, very deep JSON thing that they were inferring a type for, and discovered that at 7 levels, all of a sudden, something wasn't being checked in here because, well, the turtle cut off. Anyway, those are sort of some of the crazy things that you end up looking at. In fact, someone actually put up a GitHub issue proving that TypeScript has a Turing-complete type system. And he has, if you want to really geek out on types, go look at this issue here. He's actually creating types that can add and subtract and multiply numbers at compile time in the type system, so that's how expressive it has gotten. I wanted to talk a little bit about, some of the things that make the types themselves novel and interesting, the novel type constructors here. You're all familiar, of course, sort of with one of the basic type constructors we have, which is object types, X:(T) and Y:(U) up there. But over time, we have added more and more of these type constructors. We've added union types, intersection types, index access, and so forth. And I'll give you some examples of what these are and how it is that this makes it a very different type system. So at the very bottom of JavaScript and TypeScript, we have values. And that's sort of where JavaScript's runtime dynamic type system and TypeScript's static type system meet. They meet sort of at the bottom where there are values. JavaScript programs are all about producing values and writing logic that can make new values out of existing values, right? And there are groups of values in there, like strings and numbers and trues and falses and whatever. Now, in TypeScript, all of these values are also types. There's a type called 42, and it has one possible value, the value 42. And these are called unit types, and everything sort of comes from that. And then there are different categories of types. So the string type is actually all unit types that are strings, and the number category is all unit types that are numbers. And then we have type constructors that allow you to make more complex types out of that, like true or false. That is actually exactly the same as the built-in Boolean type. It has 2 possible values, and it's a union of either true or false, right? And that's sort of how everything builds up, if you will. Here's another type, 0 or false or undefined, and you can make types in any combination you want. This is very unlike C# or Java, where everything is sort of single-rooted and then there's a base class and whatever. That's not how this works. This is really more like reasoning about sets of possible values. That's really what the type system is doing. And of course, it gets particularly interesting here, like you can build types like string or number or undefined, right? And union types are this deep enabler that we use in control flow-based type analysis because we understand now what JavaScript statement constructs, what effects they have on types. If, for example, I have a variable whose type is string or number undefined, say it's x, call it x, and I say if x, open curly, well, we know that construct removes the type undefined because that would not execute. And that means we can restrict the union type down to string and number. And that's this narrowing that control flow-based type analysis does. And that's really, in a sense, where the type checker magically knows what values could your variables have, and it can prove, this is the deep enabler for non-nullable types, for example, and many other features in the language. We also have this feature called intersection types, which are, in a sense, just the opposite of union types. Imagine we have two types, A:*string and B:*string. When you define an object type A:*string, you're really just saying this is any object that has a property named A of type string and then some other set of properties that is unconstrained. So you're basically dealing with an infinitely large number of possible objects, but they all have a property of type A that is of type string, or named A. And the same for B. But now we get intersection types, which is, those objects that have an A and a B. And some people have sort of commented, why is it that when I intersect two object types that I end up with a union of the property names? Well, it's because you're actually constraining it more. For every property declaration you add, there are fewer possible values, right? The most possible values is curly. There are no constraints on any of the properties. And the more declarations you add, the more you're actually constraining the values, and the smaller the set gets. And that's why it's an intersection. So this is sort of the mental state that if you want to understand the terminology of why the type system looks this way. Now, over time then, we've added a bunch of interesting new type constructors like index and index access types were added in the last year or so. And this is the ability now to, in the type system, reason over the names of the properties of an object. So here, for example, I have a foo type that has 3 properties. And we have a built-in type operator called keyOf that allows you to say, what are the possible names of properties of this type? And that'll give you a union type A or B or C. Those are the possible string names of those properties. We also have this thing we call index access type, where you say, I'd like a type that is the same as the type of the A property in foo. So you can reach into things. That is an index access type. But remember again that this all operates on sets. So if you have a foo type and you index it with key of foo, well, that means you're now saying it's going to be A or B or C. I don't know which one it's going to be, though. But if I index a foo with an A or B or C, what type would I get? Well, you would get a number or string array, right? And so you see how we're operating on sets all the time, and we're trying to figure out, what are these things? And so you're going to ask, why is this useful? Well, because there are lots of patterns in JavaScript where you pass around objects and property names, and then you want to fish out the property by that name. It's parameterized. Like, for example, a get property method. This is how get and setting properties in React works, right? But you need to now be able to reason about that at a higher level. So you want to be able to say, here's a get property that takes some object T and some key that is whatever the permissible property names of T are, and it returns a T sub K. But we don't know what T and K are yet. But once we infer it, then we would like to type check it accordingly, right? And so here, if I declare myself a variable of type foo and some key, then if I say get property of foo comma A, then we know, now we can infer type number for A, and we can infer an error, or give an error because we know X is not a valid property name. And we could even say, if you give us something that is an A or a B or a C, well, then you're going to get a number or a string array. So with these type operators, we can now actually start to give types to patterns that occur in JavaScript libraries, and therefore we can finally give you better statement completion. And map types are sort of the same idea here, where you can make a function that creates a record type, where you pass in the names of the properties you want and the value that you want to put in each property, and then we can strongly type understand what comes out of it. And you can also write crazy things like wrapping a proxy around an object and have us understand how this all pans out. So here is, for example, a thing that wraps a get and set proxy around every property in an object type. And now if I give you an item here, then I get back something that has the same properties, but each property has been turned into a getter or setter of the same type, which is something that also happens a lot in JavaScript frameworks. Now, part of what this all turns into is sort of like us having to actually reason a lot about these higher order type equivalences. That's really what our job becomes, you know, and we understand, like the compiler understands all of these higher order type relationships. This is the part that gets hard for the compiler implementer. But behind all of this crazy type theory, there's actually some really useful real-world applications, and this is what powers all this excellent statement completion that we can provide. And the latest addition to the family here is conditional types, which allows us to express non-uniform type mappings. And I'll give you some examples here. Let's say I have 3 types, name, ID, and check. And let's say that they represent labels that I want to put in my UI. I have a certain kind of UI element that's called name that I use for strings, and IDs I use for numbers, and checks I use for Boolean values, right? Now let's say I want to write a function that takes some value and creates the label that corresponds to that value. Well, now I would have to write a whole bunch of overloads. I'm sure some of you have written overloads like this where, hey, if you give me a string, then you get back a name, and if you give me a number, you get back an ID, and if you give me a Boolean, you get a check. But then, of course, you might give me something that is string or number or Boolean, in which case you get one of the others. In fact, it's not even complete here, because you might give me just string or number, in which case you should only get name or ID back and not check, because it couldn't be that, right? And so you see how this can very quickly get unwieldy to try to write a whole bunch of overloads. And really what you want is sort of the ability instead to express it in the type system more directly. And that is what conditional types enable you to do. So here we can declare a label for type. So I give you a T, and then when T extends string, I want you to give me back name. And when T extends number, I want to get ID, and when T extends Boolean, I want to get check. Otherwise, this should never happen, is what this type says. And now I can declare create label as just, it takes some T, that is a string or number or Boolean, and then it gets back a label type that corresponds to that type, right? And now, it's just sort of, I don't have to write overloads, it just comes out of the types, if you will, right? That if I give you Joe, you get a name and blah, blah, blah. But if I give you, say, Joe or 42, well, then that's a string or number, so you're going to get a name or ID back, right? Because we understand how the types flow. And in fact, we will spread union types over, we will distribute union types over these conditional types. So that last, the D and E examples are interesting because the type that goes in, that we infer in, is number or string. And then we apply that to each of number and string and produce a resulting union type out. So if you give us a union type in, a union type comes out that has been mapped for each individual element. So this cleverness you can use, we can use to create interesting types, like a thing that reduces a union type or extracts stuff from a union type. So for example, here, if I have a string or number or some function type, and I exclude function, then I get just string or number, or if I extract function, then I get only the function parts of it. But now I can make a non-nullable of T that gets rid of null and undefined from some T, and that's actually quite useful. Also, we support the ability in conditional types to infer constituent types. So say I want to write a flatten or a smoosh of T operator. And this one says, if you give me an array, then please infer the element type of the array and give me that back. Otherwise, just give me back the type that I gave you. And now, flatten of string is just a string, but flatten of number array is a number. And so you can actually do some interesting reaching into types. And this turns out to be very useful for creating a very wanted type operator called return type. Say I have some function type, and I want now to get the return type of that function type. Well, you can create a conditional type that reaches in and gives you that. it's useful, like, let's say I have written some function that returns some complicated object literal. Well, return type of foo will give you back that type. And in fact, we can now build all of these into lib.d.ts, the predefined types. We already have partial read-only and pick and record that some of you may have seen. But now in TypeScript 2.8, we've added exclude and extract, non-nullable, return type, instance type, and so forth. Okay, so that's a lot of slide work. Let me try to show you what this looks like in action. So let me switch here and try to and just show you some code. I was trying to come up with an example that really sort of shows all of these features in one. And imagine that you are writing a framework that does sort of meta-programming in JavaScript. It's actually a fairly common thing. Let's say you're writing a framework for implementing services. Okay, that sounds like something that we might all end up doing. It's very common in JavaScript to use the programming language itself to define your metadata. You use object literals to describe some data, right? Like the types for a JSON object or whatever. And you can even here, for example, describe what a service is. We have a service that has 4 methods or requests that it handles: open, insert, delete, and close. And an open takes a file name of type string, and an insert takes a position, et cetera, right? That seems pretty reasonable. Now, given something like that, you might then want a function, say, called create service, where you give it a service definition, and you give it a handler where all the requests go to, and that handler just receives like an object with the parameters in it and is supposed to return some value, right? But inside the handler, you get it just as messages, right? So there's some mapping of your types that has to occur here. But then what you get back also is you want some object that is callable and has all these methods on it. And so first I'm going to show you how. You'll note here that there's not a single type annotation anywhere in this code. Yet everything in here is strongly typed. So first of all, the compiler, of course, can infer a type for service definition. But then, in the create service method, yes, we take a service definition. But notice then how the request object here is actually a transformed version of the inferred type. So we've inferred a type from service definition, but then we've transformed it into a request object that has open with a payload, insert, et cetera, in here. And when we're writing the code, we actually have here strong types. So we know that request.message is going to be open or insert or delete or close. And when I'm typing in here and I say request.message request.payload.file name, we know that that's a string. So yet we didn't write any type annotations. This all got inferred automatically. And likewise down here, where when I say service dot, we know that service has 4 methods that I can call, like close, and close takes no parameters, et cetera. So you're going to wonder then, well, where did that come from? How did this happen? Did we build this into the compiler or something? No, we actually declared it using some of these interesting type constructors. So here's our create service method that says I take a service definition, and then I take a request handler, and I return a service object. And if we now scroll up to the magic here, let me first preface this by, this is not something that you necessarily have to understand. This is something that the framework author has to understand. But there's only one framework author, right? And then there could be millions of users, right? And that's really, in a sense, what we're targeting here, right? But we need a type system that's strong enough that someone can do this, right? But once someone does it, everyone gets the wonderful experience where they don't have to write type annotations. It just magically comes out of the system, right? So here we're saying a service definition is an object that has a number of properties, that are all method definition. And a method definition is either a string constructor or a number constructor. And those are just the types of the built-in string and number classes in JavaScript. And then we say a service object is a type where you give it a service definition, and then it returns an object that has service methods. And the methods themselves then use a conditional type to say if it is if the service definition is curly curly, then you get a function that takes no parameters. Otherwise, you get a function that takes a request payload, and a request payload in turn maps types from constructors using, again, you see here a conditional type, right? I'm not going to drill into all of it, but suffice it to say that it's possible to write these, and it's not even all that many lines of types, right? And then get these wonderful experiences here. And this is actually how React and Vue and Angular and all of these framework typings work. And this is how we can keep capturing new ground in better statement completion and better type checking. It's an interesting pattern, by the way. Here's also a very functional pattern where you see that we get a request that has 4 possible values: open, insert, delete, and close, right? And what if we wanted to validate that we've handled all the cases? Well, if you observe one thing, let's say we add a default case here, okay? And in the default case, we say request. You'll see that it has this funny type called never, because the type checker has figured out that, well, you've handled all the cases, so you're never going to get here. And so that's what it uses the never type to signal. But notice that if I forgot to handle one of them, like the delete guy, and I now look at what's the type of request, it knows that it's delete, because you handle all the other ones, but you didn't handle delete. So if you're in the default case. Now, this we can actually put to good use by inserting a, where is that here? Let me insert this funny function that says, here's a function called assert never that takes an object whose type is supposed to never happen, and it never returns, and it throws an exception if you ever get there. Now, in here, we can then say assert never of request. And this is basically sort of a bottom thing that if something goes awfully wrong, we're going to end up in this default case. But the type checker knows that you're not supposed to get there. But if you forget one of the cases, then immediately it tells us here you forgot about close, because you ended up down here because you didn't handle all the other cases. And now all of a sudden you see how this is actually sort of like pattern matching in functional programming languages with exhaustiveness checking. You know, that's all based on just JavaScript paradigms and type inference and so forth, because this is probably the kind of code you would write, because you've got to be defensive about handling these cases, even though they're not supposed to happen. They might happen if someone's calling from JavaScript and so forth. So anyway, those are some of the cool and interesting things you can do with conditional types. Let me move along here and talk about some of the other stuff that has been going on. Where's my clicker? There. We have this mode. How many of you are familiar with strict mode? This is a mode that we also introduced, that's a good number, in the last year or so. And strict is basically this, this mode that is going to just check as hard as we possibly can. And it's actually a mode that is a whole bunch of compiler flags bunched into one. Now, there's an interesting dilemma when you're writing type checkers, which is what we do for a living here, right? Which is, it is actually our job to break your code, right? It's our job to deliver error messages. That's sort of one of the things we deliver, right? Yet, you want to be able to get the latest version of the compiler, but you don't want to get new error messages, right? So, well, but then aren't we done then? I mean, and so how can we do new things without breaking your builds, right? And that was a problem that we thought about for a while. And the place we landed was, okay, going forward, every new feature we do, we're going to put under a compiler flag. And you don't get that feature unless you opt into this compiler flag. So you don't get strict null checks unless you opt into them. You don't get strict function types. You don't get whatever. So you can just grab the latest compiler and it'll still work the way it used to. However, and then you can, over time, opt into the new features, right? And that's great if you don't want breaks. But another way you can tie yourself is you can say, I'm going to turn on strict. And what strict does is it changes the default of all of these compiler switches to be on. And now you've opted for maximum pain on every release, right? But also, we're gonna check your code. Every time we ship, there might be breaks because we check better. But you can start with strict, and then you can, when you get the new release, you go, oh, there's some new errors. Well, let me then turn off some features. So you can either start from get me everything and then selectively opt out, or you could start from I want to have exactly the same and then selectively opt in by not using strict. And that's the intent of strict mode. We do encourage people to use strict mode because there are more and more features that you get, and a lot of these features are really, really useful, like strict null checks, and we really recommend that you do that. I'm going to show you a couple of the new strict features that we have in that we've introduced in the last year. One of them is strict function types, and here's a small little hierarchy of interfaces: pets and dogs and cats, and then we have some function taking pets and dogs and cats. Okay, and it is certainly always safe to treat a function that expects pets as a function that you can give dogs to, right? That's fine. You can call me with dogs, and they can be treated as pets. Now, what's surprising here is that this is allowed. What if I have a function that expects dogs, but I treat it as a function that you can pass pets to? Well, that might be okay, but it also might not be okay. And we used to default to allowing this for a variety of reasons that have to do with co- and contravariants and array types. You want a string array to be assignable to an object array, but that's actually not safe. Because if you take a string array, assign it to an object array, and then start pushing objects in there, well, it's actually a known hole in C# and Java, and they emit a dynamic runtime check, in order to give you covariant array types. We could plug this hole, but it would be a very painful world to live in because now your arrays would become invariant and whatever. But so we're not doing that. But for function types, we actually could do better than we used to. And let me try to turn on strict mode, and then you'll see that in this example here, whoops, I close it. Once I turn on strict mode, you'll see that where we previously did not error here, we now do give you an error. And likewise down here, when you do higher order functions where you have a function that can combine functions, where you give it a list of functions and then it gives you back a new function, and when you call that, it calls each of the functions that you gave it. Inferring types for that, when types occur only in contravariant positions, you actually have to infer the other way around, and that's what we do in strict function types mode. So suffice it to say that that's one of the stricter features that you get, and that's great if you're using a lot of these functional libraries that are out there. Another one is strict property initialization checking. If I turn strict checks off, oops, like this, and let's go back to person here. You'll see that here's some code that pretty obviously is not going to work so well, because I say I have a person that has a name property, and then I new up a person, and then I say p.name.toUppercase, and that's going to go because name was never initialized, right? And a lot of people asked us, can you please check that I've initialized my properties? And that's what strict property initialization does. So when you turn on strict property initialization, or you just turn on strict mode, you'll see that you get an error here now that says name has no initializer and is not definitely assigned a value in the constructor. Now, we actually also offer up some fixes. So you could say, oh, well, add undefined to the type of the property then. And then you see, now the error moves somewhere else where you say p.name.something, and nope, can't do that. So maybe that's not what we wanted to do. Maybe we did actually want to write a constructor that takes a name colon string. And in here we say this dot name equals name, for example. And now it works, except now we get an error here that you need to give me a name, which I could do, or I could, but let's say it's optional to pass it. Well, then we're back to here where, wait a second, you can't take something that could be undefined and put it into a field that okay. Well, then let's try to say if name, then initialize it. Otherwise, well, now the error went up here. You didn't initialize it in all of the possible code paths in the constructor. And this is something that we use control flow analysis to check. This is the same logic that we use inside functions to figure out what's the type of a variable. But here we actually check your instance variables, and we check all the possible code paths in the constructor. And here it's obviously possible for the constructor to exit without initializing this property. But if we were to add an else clause, then we would be fine, because now we've handled all of the possible code paths. Now, let me actually use another one of our capabilities, which is extract to method. Let's say all of my initialization code sits in a method called init, like so. It's a fairly common pattern that people do, right? Well, now we're back to whining at you about, like, you didn't initialize in the constructor. What you can then do is you can use what we call a definite assignment assertion, where you just put a bang here and you say, never mind, I got this one. Just don't bother me about this guy. It's sort of like the bang that you can use in expressions to to get rid of nulls when you know for sure, but the type checker can't quite figure it out. Except you put it on the declaration and you just bang away. So it's sort of part of your type annotation, if you will. So that's strict property initialization, also quite a useful feature. Let me try to go back and talk a bit more about some of the other things that we've done. Refactorings. This is, over the years now, we built up a very solid base of information knowledge in the compiler. And now we're committed to, in every release, turning that into cool and useful refactorings. And we've added a lot in the last year, and you should expect us to see us add more in every one of the releases that are coming out now. I thought I'd give you a little rundown on some of the interesting ones that we've done in the past year. So let me try to go back to my machine here, and let's go to a different project. Yep. Here's a little 2-module program. We have a module called shape that has an abstract class shape, and now we're going to implement a circle that implements that shape. So we're going to say class circle extends shape, just like that. And you'll see there's an error here that says, if we hover over it, it says, can't find name shape, but we also offer up a quick fix, which is one kind of refactoring, right? Where it says automatically add the import statement for that guy. And so we can check, and if all of your modules have something called shape, then we can automatically import it for you. The other thing you see here is that we have an error that says you're not implementing all of the abstract methods, but we have a refactoring that says implement inherited abstract method, and then we automatically write methods for those. Now, let's say in here then that we declare a constructor that takes a radius colon number. Colon number, curly curly. You'll see that there's actually, there's an error here, which is we have to call super, and we didn't. So we have a refactoring that says add the missing super call automatically. And then let's say you say this dot radius equals, and let's say I misspelled here, for example, like so. You'll see that first we give you an error here, but we also now actually support what's called Levenstein difference. So whenever there's a misspelling, we look in all the identifiers that are in scope here, and then we find the one that has the closest spelling, and we suggest that in a refactoring. So we can automatically just change the spelling to the correct spelling. And then there's another refactoring. We didn't actually declare this radius property. It doesn't exist, but we have a refactoring that can automatically declare that for you. Likewise, if we go about implementing it, say return math.py, there we go, times radius. And now if I statement complete on radius, you'll see that we automatically insert this dot radius, which is quite handy because you're writing that a lot when you're doing classes. So those are just some of the refactoring. Some of the new ones we've added is, say I write a function hello of x comma y. That, for example, says just return x plus y. And then let's say I have here I did not add, and I'm in strict mode, so we're complaining that it implicitly has an any type, but there's actually now a refactoring that we offer up that says infer parameters from usage elsewhere if you can. And here we see that you're calling it with number, so we can go infer that and then offer a refactoring that automatically adds these. And indeed, you'll see that if I called it with, let's say, foo, comma, true, also, somewhere, and then we try to ask for inferring, then we pick that up, right? So that's really useful when you're coming from a JavaScript code base and you're adding type annotations. There's a lot of places where you can just automatically have us infer it this way. We can actually also infer from the body. Since you are in here, let's see, let me try it off of this. Here, there are no calls, but you're sort of constraining it because you're using the plus operator, and the plus operator would only work if they are either strings or numbers. And so we can also infer from the body in cases we don't see any calls. Likewise, let's say you had written JS doc annotations for your code, like so, and then we can actually annotate by bringing down the JS doc types automatically. And that, again, is super useful if you're in a JavaScript code base and you're moving to TypeScript. So, and we're committed to doing more and more of these because these are sort of like the things that make you more productive. Okay, let me switch back here. And let's talk a little bit about, I mentioned this earlier, that we are actually using JavaScript as or TypeScript as the JavaScript language service. And I wanted to, this we do by running this thing called TIA server out of proc from your editor, and we have this language service protocol that we talk to TIA server. But the cool thing is really that you can actually do get some really nice benefits from TypeScript without even using TypeScript. Let me go here we have a completely empty directory. And then we first npm install Lodash, and let me npm install jQuery, just so I have a couple of things installed in here. And then let me try to fire up code, and let me add a new file called main.js. And then let me just start typing whoops, it may need to, there. Let me just type $, and magically you get statement completion. I mean, Where did that come from? You might wonder, and some people do wonder. Because we automatically scrape and deploy all definitely type definitions into NPM and put them in the @types namespace, we can actually look at your node modules folder, see what modules you have installed, go out and consult NPM to see if there are types available for them. And if there are, then we can auto-provision those types and just bring them down so we can give you statement completion. And that's what's going on here in the background. So we notice that you have Lodash and jQuery installed in node modules, and so we go grab types for them and put them in a cache that we maintain. It doesn't interfere with your project at all, but now we can give you great statement completion, which really is super useful when you're writing JavaScript. Here's like Lodash, and now you'll note that we can even start flowing types here. I'm using filter in Lodash, and then I say, here's the filter function, and we know that X in here is going to be a number because you gave us an array of numbers, right? And this is in JavaScript with no annotations whatsoever. I could also, in fact, let me try to write another function foo here of x comma y. And let's say I return x plus y in here. And let's say I annotate this one with JSDoc, where they're both strings, like so. We can slurp up these annotations, so when I say x dot, you'll see that we can give you statement completion because your JSDoc annotation said that you were strings. So that's something that we also automatically do. But of course, if I return x times y, it's kind of weird. We know they're strings. This is never going to work, but we're not telling you anything. And that's because by default, we don't give you error messages. We just give you statement completion, and we just try to help you as you're writing your JavaScript, but hey, it's JavaScript. But we now actually have a mode that you can opt into by adding a TS_check annotation in your code that says, hey, why don't you try to type check my code and just infer as much as you can. Run it in a more lenient mode where if you're not sure, then just let it go. But in cases where you absolutely know this is going to go wrong, give me an error. And now you'll see all of a sudden we get errors down here that, hey, this isn't going to work, right? These you can't multiply strings. And also, if I misspell something here, we get errors, because we know for sure this is going to be a number. Numbers do not have methods named that, right? But this is entirely optional. And you see that there's sort of this very gradual slope, and you can just opt into as much as you want. And then you can eventually end up using TypeScript in its fullest, but you certainly don't have to. So that gives you sort of an idea of how that works. One thing that, an interesting thing that happened is that a very well-known project called Webpack recently switched to using this mode. There was a pull request to add TypeScript type checking to Webpack, not by adding type annotations and switching Webpack to .ts files or anything, but rather just by turning on TS_check in all of the source files. And the magic thing is, once this guy from Lyft, Mosen, did this work, he actually found several bugs in Webpack just by turning it on. And what I've done here is I've reconstructed that code, what the code looked like before before the bugs were fixed, okay? So just so you can get an idea of what it looked like when the compiler found the bugs, okay? So if we, let me just do a build here. Now, Webpack's build process now uses the TypeScript compiler, but in no emit mode. So it doesn't actually emit anything, it just type checks. And now they're gradually adding JSDoc annotations to the code base. But bugs that we found right out of the gate are like, hey, you're assigning to properties that you never initialized in the constructor. Okay, that's not a super terrible thing to do, but you know, we actually even offered up fixes here where you know, you could just automatically say initialize or fix. Let's see, fix all in file here. Oops, no, that's not what I wanted to do. Okay, let me go back here. Let me try to say. Initialize them all in the constructor, and now let's go look at the declaration, and you'll see that we've inserted some declarations for you automatically. Let's try to look at some of the real bugs that were found. This one was actually kind of nasty. You see how this is a function called cast merged that returned cast merged of whatever, and then it calls itself recursively, except it also declares a local variable cast merged here that isn't a function. So this thing would blow up if you ever entered the recursive loop, but they didn't have test coverage for that, but the checker found it, and they fixed the bug, of course. There were other similar errors like that. I'm not, you know, passing too many parameters to functions, using weak maps with string keys which isn't supported, and so forth, and all these things we found simply by checking. And of course now, once they start adding more JS-doc annotations, we're gonna keep finding issues. So that's the JavaScript with superpowers. The last thing I wanted to show you is where we're going for TypeScript 3.0. One of the things that we've been hearing more and more is that my TypeScript projects are getting really big. I have this mono repo that is like 20 TypeScript projects that are each very big, and I can't compile it all as one, yet I would still like to have all of the IDE services available, and I sure would like some form of incremental build, and I would sure like to be able to navigate from one project into another instead of navigating into its declaration file and so forth. And that's some work that we're now doing. I'll actually try and show you just as an example. Let me try to look at the slides here again. I had this is the problem that we're trying to solve, right? Imagine, I'm just going to look at the compiler project, or maybe explain to you here briefly how the feature is what we call composite projects, and it allows one project to reference other projects in its tsconfig file. So here we have like a core project that doesn't use anything, a services project that uses the core, and then an app that uses the services. And you see how they each have a references property that references the one that's one level up. Once you are a composite project, we are a little bit stricter about you must specify in your files or include or exclude masks the exact set of files that constitute the compilation. But once you do that, then we can very quickly check whether a project is up to date. And that means that we can do incremental builds in a much more efficient manner. And one example of that is actually the compiler itself. Today we build the compiler 5 times, and it takes, you know, a minute plus to just, and so we're feeling it on our own bodies, which is good for you because that means we're motivated to solve the problem, right? And this is what the compiler actually breaks down to in terms of nested projects. And I'm going to try and show you here. Just let me go to TS, and then let me just do a build. I'm going to use PowerShell to type it, to measure the execution speed. So I'm going to do a build with and pipe the output. Switch? Oh, sorry. Yes, there we go. I'm just typing away. I'm going to build the compiler, which is going to take a little while. But then meanwhile, I could go back to the slides and just talk about how, and then we'll come back and look at how long that took. The compiler is used by 5 different deliverables, and I'm sure you have projects like that too, where there's some core library that's used by 5 different deliverables in your app, the server side, the client side, et cetera, right? yet you don't want to build that 5 times as you're doing your builds. And so you probably set up build scripts and whatever, but if you do that, then you end up just with a DTS file now, right, that you're referencing in your other projects. And now if you say go to definition there, you just end up in a DTS file. You don't go to where it's really defined, right? So you really want the compiler to have a deeper understanding of how these projects relate to each other. And that's what composite projects are about. And so if we look at here, try to go back to, it's still grinding, but I think we're getting there. There you go. And that took a minute and 6 seconds. Let me now try to switch to a Hive here, where I have a refactored version of this same compiler. And I'm going to start by first saying measure command of TSCX with the force switch. And now I'm going to force it to just build everything in this Hive here. And you'll note that first thing it does is it builds the compiler, which is a big component, takes a little while, and then it starts building all of the things that depend on the compiler, et cetera, et cetera. And this ends up taking about, I think, 30 seconds or so, which is already faster than we were before. But let me now try to modify in here, and I'll just make a special version, a build version of the compiler here. Just so I modify one file, which is just the compiler, or one project. And let's try and build here. And now you'll see that, yes, we rebuilt the compiler again because I made a change in that source base. But then all of the other projects will notice that the compiler's declaration file didn't change, and therefore we don't need to rebuild those. And now we're down to just 12, 13 seconds rebuild time. And this is something that we're going to build into the entire infrastructure. So it's going to ideally work with go to definition and rename across projects and whatever. But I'm not going to promise that it all surfaces in 3.0, but we're certainly moving towards that. Okay. Final slide really is just a summary of our value system. And again, I want to really urge you to participate in the TypeScript projects on the issue tracker. If you're using typings from Definitely Typed and you find bugs in them, please fix them, submit pull requests, make the world a better place to be. But thank you very much for coming. I guess I used all of my time, so I won't be doing answers, but I'll be around here. You can come up and ask questions if you like. And thanks again. Please fill out an eval form, and thank you.